This is a part of the topic on forces, but also it draws in ideas and energy as well. So this is about the stopping distance of cars. Okay, so what happens? Well, when a car is travelling along, I'll do another one of my terrible cars here. When it's travelling on a certain velocity, it will take a certain time to stop. And that's a combination of times. The first bit is how long it takes for you to think, I need to stop and hit the brakes, or you see a red light in front of you. So the first part is the thinking distance. And then you need to add to that the braking distance. How long does it take for this car's kinetic energy that it has here to turn into the work done in the brakes? And ultimately that work done in the brakes turns to heat. And so therefore you have the distance in terms of thinking, then you have the distance in terms of braking, and add those two together and that gives you the stopping distance. Now of course lots of factors are going to affect this. First of all, so let's just list the factors. Okay, first of all, for the thinking distance, you have, drink and drugs are significant factors, but more importantly and topical these days, mobiles and other distractions. They can say that children in the back of cars are causing many distractions as well, just as bad as having a mobile phone out. Braking distance, of course, depends upon the kinetic energy of the car, so that depends upon the speed very much. I suppose both of these depend upon the speed in actual fact. But this one particularly with the speed, because as you know with the kinetic energy is proportional to the velocity squared, so it's much more significant with the speed. It also depends upon the mass of the car. It also depends upon how good the brakes are. And, of course, the conditions of the road. Not the driver this time, the conditions of the road. So all of those factors must be taken into account. However, once they have been taken into account, you can get a very nice sort of velocity time graph showing the stopping distance of a car. And it goes like this. In other words, you're going at a constant speed and it's taken this long for you to register that you need to brake, and we'll give this approximately 1 second. I think reaction time is like 0.7 of a second, but we'll just say it's 1 second to make life easy for us. And then I'm going to say it then takes 5 seconds in order to come to a halt. And let's say we're moving at 20 meters per second, which is quite fast, about 70 miles per hour, something like that. Okay, first of all, what is the thinking distance? So remind ourselves again, thinking plus braking equals stopping. And of course, when we dealt with velocity time graphs and forces of velocity time graphs, you know that the distance travelled on a velocity time graph is the area underneath. So the thinking part is this area. The braking part is this area, giving us a total. So what is the thinking area? Well, it's the area of this rectangle, 20 times 1. Okay, what's the area of this part here? Well, that's a triangle, but it's 20 by 4, the difference. And obviously it's a half times base times height. So that gives us 20 plus 40, giving us 60 meters. That's how long the distance it takes to stop. Interestingly as well, what about the deacceleration of the car? What's that going to be, the deacceleration? If you think you know, hit pause. Otherwise, here we go. Here comes the answer. Well, deacceleration or acceleration is the change in velocity over time. So whilst it's braking, I've gone from 20 meters per second to 0, or minus 20. And that's occurred in the difference in time here. The difference, which is of course 5 minus 1, which is 4. That gives us 5 meters per second squared. That's the deacceleration, or minus 5. So it's a deaccelerate by 5 meters per second squared. And I suppose to make this nice and synoptic and bring everything together, let's say to ourselves that the car we're dealing with is 1,000 kilograms, 1 ton car, just to make life nice and easy. What is the kinetic energy of the car? And then what's the average force from the brakes in order for this to stop? If you think you know, hit pause. You think you know the first bit, then go for it, and then I can tell you to hit pause again for the second bit. Okay, straight away for the first bit, kinetic energy is half mv squared. So let's substitute that in. Half times the 1,000 kilograms times the 20 meters per second squared. We're at 20 here. What does that give us? Well, off the top of my head, no, something I calculated before. It's 200,000 joules of kinetic energy this thing has. So what happens to the force in the brakes? Well, can you remember the equation for work done is force times distance? If you can, now hit pause and see whether you can work out the average force of the brakes. If not, here goes. Well, when we rearrange the equation, we know that force is work done divided by the distance. And as I said before, in order for this to come to a halt, all the kinetic energy must have converted into the work done in the brakes. So we can say to ourselves that the work done is actually the kinetic energy. And the distance, of course, is something we've found out, which is, it's the 40, because that's what's happening in the braking distance. It's this area here we're interested in. So divide that by the 40 meters, and that gives us 5,000 newtons as the average braking force. Okay, hope that made sense.